Hoa will just do whatever you say.
Okay,
we will follow all your instructions.
Okay, so I think we should start now, and then I think the video is recorded, so everyone be notice that. Welcome everyone to the seminar this week. Coming with us this week is the famous Alex Kruger. He's too he's too famous that probably we don't need my introduction, because everyone here probably know Alex better than I do. But because I'm his best favorite student, that is why I'm going to do the introduction. So Alex usually say many strange things as we usually know. For example, he's always say that he had two lives, one in Australia, start from 2003, and another one back then in Minsk, Belarus. So I didn't understand that. But then I figured that, well, that might make sense because maybe the personality probably changed. So I collect some evidence for that. And on those, his life changed, but his research remained very consistent, which proved his endless love for price analysis. That is why he coming with us today and present about error bounds. So he will keep preaching if we don't learn anything. So please, everyone, do learn some things. So Alex, now the stage is yours. So educate us.
Thank you, Hua, for your introduction. I've just learned a few new things about myself, and it was interesting, entertaining. Also, you are learning not only mathematics. Okay, good. My apologies, first of all, to those people in the audience who came here to listen to the talk by Valentin Gorokhovik, who was scheduled for today. Unfortunately, he was unable to give a talk today, and I am using this time slot not to lose it. But Valentin's talk will be presented in due time. Preliminarily, it is scheduled for May, as far as I know. And by the way, our list of talks is getting filled very quickly. So if someone wants to present, be quick to volunteer. Otherwise, there will be no vacant slots. My presentation today is about error bounds. And I've already made quite a number of talks on this topic, on error bounds, and have written a few papers. And at some stage, I decided that the topic was closed. I didn't plan to continue working on this topic. And then it was an initiative of my co-author, who is here, Nguyen Duy Quong, a student at our university, PhD student, who pushed me back to this error bounds environment. He got interested at some stage at this stuff. And of course, this stuff is very strongly connected with many other topics. And I, at first reluctantly, but then with enthusiasm, moved to my old area of error bounds. Today, I'm going to present something which is not just some new results in this area. It is very difficult, by the way, to find something new in this area where so many people have worked. It is more about presenting a general scheme. So in the process of us, King and me, working on this topic, we gradually came to understanding that there is already some general scheme, general hierarchy of various error bounds characterizations, conditions. And today I'm going to make emphasis not on new results, but on clarifying the relationships between existing ones and presenting some general scheme. although a few things are going to be new, I hope. So, the outline is pretty short. I will remind a little bit about error bounds in general, and then I will continue into presenting this general scheme, starting with linear conditions and moving a little bit into the nonlinear environment. And I'm going to make a point that nonlinear, seemingly more general environment can be viewed as a particular case of the conventional linear theory. So let me start with definitions, and first of all with people who have contributed to this area. This is a very short list of names. The actual list is definitely much, much larger. And I must say that when preparing for this talk, I wanted to add a few recent publications. So I had to remove certain lines which existed here in my previous publications. So now we have to make choice. So the area is huge because of numerous applications. Error bounds are everywhere in convergence estimates for computational algorithms, in penalty function stuff, optimality conditions, constraint qualifications, although in theory as well, like qualification conditions in subdifferential calculus, and many, many other things. I think that there is not much sense to provide motivation. People are familiar with numerous applications of these things, possibly under other names. So when talking about error bounds, I mean this definition. So we are in a setting of a general metric space. F is an arbitrary function at the moment. And I want to emphasize that in this talk, I'm considering only the general setting. So this function will be assumed at most lower semi-continuous, no other assumptions, which to some extent limits the boundaries of the topic, because many people are interested in the opposite, considering specific functions arising, for instance, from optimization and formulating some conditions for error bounds for such functions. So I must apologize, this topic is outside the scope of today's presentation and also outside the scope of our joint paper with Kruger. The number tau, positive number tau, plays an important role here in this definition, and we are talking specifically about tau error bound. Tau is a positive number. In the inequality, here in the definition, I put tau on the left, although it is pretty common in some publications to put it on the right. There are advantages, disadvantages, but you should see that these settings are equivalent. Using tau or its reciprocal, this is the same thing as long as we're in the linear setting. In the nonlinear setting, there can be some minor differences, and hopefully I will talk about it a little. So the idea is to estimate this distance from some point x to the solution set of a single inequality. I'm using this notation, which is more or less accepted already notation. This set denotes the set of all x's where the function takes non-positive values. So we are looking for solutions of this single inequality. And if X is not a solution, we are trying to estimate this distance in terms of values of the function. Of course, f of X is positive because X doesn't belong to this set. And this is given explicitly here. F of X is greater than 0. And this inequality is required to hold in some neighborhood of the given point X bar, and also in some area, satisfying this restriction on the value of the function. This is another notation which is given here, also pretty standard notation, this one. Now, something a little bit not standard in this definition, both delta and mu are allowed to take the value plus infinity, here and here. So if delta equals plus infinity, it means that this ball of radius delta is the whole space. So X bar doesn't play any role in this condition. And we are in the setting of global error bounds. And one of the points in my today's presentation is that local error bounds and global error bounds can be treated within the same theory. Normally in publications, people attack local and global error bounds separately, and they find some differences, but mainly they repeat the same steps in the proof. So now we are combining these two settings into one. Concerning mu, in fact, mu can be removed from this definition or can be set to plus infinity automatically, and this part can be removed equivalently. However, from the computational point of view, and I was reminded about it during one of my presentations. Up until recently, I didn't care much about the values of delta and mu, just there exist some numbers. But I was reminded by computational people who are really dealing with algorithms that these numbers can also be important. They don't want to just know that some regularity condition like error bounds exists somewhere. They want to know precisely where this condition is true. And in this presentation, I'm going to produce quantitative estimates not only for tau, which is the main parameter here, but also for delta and mu. So that's why we are not removing mu. It will be present in all definitions and also in all conditions. And I'm going to talk about sufficient conditions for error bounds only, which is the mainstream of this topic actually, although some people work with necessary conditions as well. And I know that Kung likes necessary conditions, and we had also a presentation by Shaoqi Yang recently at our seminar, and he works on necessary conditions as well. I'm limiting the presentation to sufficient conditions only just for brevity because of the time limitations. In our paper, we actually consider necessary conditions as well. Okay, so this is the introduction. This is the key definition, linear definition, because we are looking for this linear estimate. Those working in this area definitely know that this property of error bounds is closely related to other properties like these two, subregularity and calmness of set-valued mappings, or subtransversality of collections of sets. And in fact, these are all just reformulations. In fact, these settings are equivalent. error bounds for real valued functions, extended real valued functions, or subregularity of set valued mappings. These two properties are in a sense equivalent, and the set one is in equivalence as well. So from this point of view, what the conditions which I'm going to present today, they are applicable to the other two settings as well. Stronger properties of metric regularity, band property, transversality of collections of sets, they're also related, but not equivalent. These are stronger properties. But if you think about them, if you're familiar with these properties, these are uniform versions. What is metric regularity? It is subregularity condition holding uniformly for some values in Y space. In fact, one of the earliest applications of error bounds around 2000, 20 years ago, error bounds were used for deducing characterizations of metric regularity. So this is like another motivation for this research. So I've chosen the simplest setting of error bounds, and I will talk about it, although this stuff is applicable to other settings as well. And an illustration. On the left and on the right, in both this illustration, the solution set, where the values of f are non-positive, is the left half line here or here. The distance, if x doesn't belong to the solution set, it means that x is positive. The distance from x to the solution set is, of course, just x when x is positive here or here. And in this case on the left, we can easily see that we are in the setting of error bounds. This inequality holds, and we can even say exactly that it holds with tau equal 1. On the left, we cannot find such a tau. Why? Because when x approaches 0, the value of the function goes to 0 much faster, and we cannot obtain this estimate. The conclusion, we don't have linear error bounds here. So this is a situation where nonlinear error bounds can be helpful. And this situation is not only of theoretical interest, it can be of practical interest, for instance, when talking about convergence. Of course, we won't be able to guarantee linear convergence, for instance, of alternating projections. But some form of convergence can be guaranteed in terms of error bounds. Now, talking about sufficient conditions, and I already mentioned that I will talk only about sufficient conditions. In the huge variety of established conditions, there are two big groups: primal space conditions, usually formulated in terms of certain slopes, and dual or subdifferential conditions. My point is that these are not absolutely different type of conditions, and when deducing dual conditions, people still have to go through the primal space part, and they do it. Sometimes they do it without actually noticing it, but if you look in the proof, they establish primal space conditions as well. And unlike the other analogs of this property, many people actually are interested specifically in the primal space conditions and don't continue into dual space ones. Within this talk, we will be in the setting of a complete metric space, and the function will be assumed lower semi-continuous. Of course, when talking about dual conditions, it means that the space is a Banach space, complete norm space, because we need linear structure to talk about subdifferential conditions. linear space, which is complete as Banach. As I already this is slightly different. We are using the same terminology, non-local, local, but here I am talking not about local and global error bounds. I am talking about local and non-local conditions characterizing error bounds. Slope conditions, normally these are local conditions, but I will formulate some non-local conditions of slope type as well. And this is like the first step in establishing any type of conditions, local, primal space, or dual space. So I will explain it a little bit later. In the dual setting, I distinguish between general Banach spaces and more specific Asplund spaces. Without going deep into the theory, probably most of you know that Fréchet subdifferentials and limiting Fréchet differentials work very well in Asplund spaces, but these conditions cannot be extended easily to general Banach spaces. General Banach spaces, we must use other types of subdifferentials. In this talk, I'm using Clark subdifferentials, but we can use approximate subdifferentials of Joffe or some abstract subdifferentials combining the two. I just want to attract your attention to some important difference between the two. Not just the fact that Clark subdifferentials are larger than Fréchet subdifferentials. They both possess some rules which play an important role in the whole theory here and in subregularity, regularity, etc., etc. The some rules are different. For Clark subdifferentials and for Joffe subdifferentials, some rules exist in exact form. I won't go into details here. And for Fréchet subdifferentials, we can only formulate so-called approximate sum rules, and it makes things different, at least slightly different, when formulating conditions. So this is the setting which I'm going to talk about today. Connections between these two conditions. Condition 1A is this part, non-local conditions in primal space setting. And it is trivial to see that error bounds immediately imply these non-local conditions, or just believe me, I'm saying easy to see, but I haven't formulated the conditions. So just trust me, it is indeed trivial to see that 1A follows from error bounds. So in fact, it is a necessary condition. But I promise to talk mostly about sufficient conditions. Another trivial observation is 1B implies 1A. Local condition, if local conditions are satisfied, they immediately trivially imply non-local conditions. And looking at this line, it looks like this part 1B is useless because it doesn't lead further to error bounds. One more remark here. With this trivial line, actually, we don't even need the space to be complete, and we don't need the function to be lower semi-continuous. These two implications hold without these assumptions for any metric space and for any function. The much more important line is the next one. In this setting of a lower semi-continuous function on a complete metric space, condition 1A implies error bounds. And now it is pretty clear that this is an easy exercise. Now it is an easy exercise. A lot of people struggled with this for years. Now it is easy to claim that this is an easy consequence of the Eklund variational principle. And this explains why we need the space to be complete and why the function must be lower semi-continuous. So as a result, we actually have equivalence here, 1A equivalent to AB. And thanks to this observation, 1B indeed provides a sufficient condition. Local conditions are sufficient. Local conditions, which I'm going to formulate a bit later, are indeed sufficient for error bounds. Now, what about dual conditions? Both these conditions, A and B, in general Banach spaces and in Asplund spaces, both imply the local condition in primal space. And from this point, they are sufficient for error bounds. These implications are consequences of the corresponding subdifferential sum rules. I already mentioned it briefly, and this is where the difference between these two sum rules comes into play, and I will comment about it a little bit later. Notice that I don't formulate any relationship between 2A and 2B. It would be natural probably to expect that the Asplund space conditions in Fouché subdifferential, in terms of Fouché subdifferentials, should imply conditions in terms of Clark subdifferentials, at least in Asplund spaces, because Clark subdifferentials are larger sets. And it is usually true, but there are some minor exceptions. I will mention them in the next few slides. And these differences result from the difference in the sum rule, which I already mentioned. Okay, so these are preliminaries. And now let me talk more specifically about error bound conditions. So let me start with linear error bounds. I'm repeating the definition, and I'm repeating these illustrations here and here where linear error bounds hold and where we don't have them. What do we need to guarantee this inequality? So we are outside of the solution set because of this assumption, f is greater than 0. And it is almost obvious that it is somehow related to the rate of descent of this function. If we can somehow bound the rate of descent of this function from below, we can guarantee that the values of the function decrease sufficiently quickly when x approaches the given point x bar. Then this is basically what we need to establish error bounds. It can also be illustrated here, looking at these pictures. Here we have the slope of the function, positive, +1, and we have error bounds. Here, the slope of the function actually decreases to 0, and we don't have linear error bounds. So the slope of the function plays some role here. So let's go into the theory of slopes briefly. A quite well-known object, which is actually called slope. It was introduced by these three people, De Giorgi, Marino, and Toskes, in 1980, 40 years ago, in the setting of the general metric space. And if you look at the definition, this is exactly the largest rate of descent of the function at the given point. So it is natural to expect the conditions for error bounds to depend on this, to be characterized by these two slopes. Another slope, which appeared relatively recently, 12 years ago, 13 years ago, is this non-local slope. Unlike lim sup here we have just sup. Of course, sup is larger than lim sup. Another small difference is here, we have plus. The meaning of plus here and everywhere is common, positive part of the number, maximum between the number and 0. Here we put plus here to ensure that when values are negative, which means that we are already in the solution set, we don't care how strongly the function continues to decrease. It is already not relevant. We don't need this in the local version, only here. And in fact, there have been several definitions of non-local slope. This one in the paper by Ngai and Tira, they actually didn't give the name. They used it in characterization, but without giving the name. And I think they didn't use this plus because the function which they used only took non-negative values, so they didn't need it. So there were a few other definitions. I won't go into details. This notation with diamond is my notation. And when the space is normed space, it can be, the rate of descent can be characterized in terms of subdifferentials. This constant distance from 0 to the subdifferential has been used by many authors working with error bounds, subregularity, regularity, in many conditions. Not many of them used to introduce a certain notation and to call it a slope. I introduced this terminology about 10 years ago, and then I found out accidentally that Stephen Simons used this notation and used even this terminology, subdifferential slope, much earlier, 20 years earlier than me. And it is also interesting to observe that he used it much earlier than people started using these slopes in optimization. This original one was introduced earlier, but not for optimization, for other purposes. I think people started using these things around 2000, and Stephen Simon introduced his subdifferential slope 10 years earlier for convex functions. So for convex functions, there is no ambiguity. I'm going to use this notation also for Friche subdifferentials and Clark subdifferentials, and I'm going to use these notations. So Friche subdifferential slope and Clark subdifferential slope. So having these three slopes, or three groups of slopes, because here actually there are two, the connections between them are given in this simple lemma. Of course, the non-local slope is larger than local, assuming that the value of the function is positive. In Banach spaces, the lower estimate for the slope is given by the Clark subdifferential slope. And this actually explains why subdifferential conditions follow from primal space conditions in terms of slopes. It is thanks to this inequality. And this inequality is actually a consequence of the sum rule. I'm not going to present any proofs, just notice that this is where one of the key results is hidden, the sum rule for Clark subdifferentials. In Asplund spaces, we can also obtain a lower estimate, but notice that in lower estimate, of course, in terms of Friche subdifferentials, and observe the difference. Here we have just the inequality. Here we have lim-inf operation, and this is because the sum rule for Friche subdifferentials is in approximate form. This is a key thing here. And it has also certain consequences for characterizations of error bounds. So one more important thing before I start formulating the conditions. We have three slopes, three groups of slopes. In fact, we have certain slope operators applied at this point, at some point. I'm going to introduce collections of slope operators. What for? My idea is to combine in a single statement several groups of theorems, which are usually formulated separately for primal space settings, for dual space settings, local conditions, global conditions. Kung and I, we formulate all these things in one statement. And the idea is to combine these slope operators into certain collections. We do it recursively. On the first step, this collection df naught consists of just a slope, usual primal space slope. If this space is Banach, we add Clark subdifferential to the collection. If this space is Asplund, we add also Frichet subdifferential. So the thing is purely notational. Of course, it allows to produce shorter statements, but this is not the main advantage. The main advantage is that we now can combine several statements into one. So in Asplund, if the space is Asplund, this collection actually consists of 3 subdifferential operators. This one, Clark subdifferential, and Frichet subdifferential. This is not all. 2 more collections. So once this one has been defined, we define one more without naught by adding this non-local slope. Non-local slope is a bit special. So sometimes we need it, sometimes we don't need it. That's why I introduced this special collection involving this slope. So this one in Asplund spaces or in finite dimensional spaces consists of 4 operators. And one more thing, taking this one, we exclude Frichet subdifferential slope operator. Frichet subdifferential slope operator is also a little bit special because of the special sum rule used in these conditions. So this one is going to play the main role. This one and this one are a little bit auxiliary. And the first statement, a lemma, I will call it a proposition, a fixed X statement. So normally error bounds are required to hold in a neighborhood of the given point for all points from the neighborhood. So now I'm going to formulate a simplified statement, not for all X, but for the fixed X, not belonging to the solution set. And the statement is a little bit long. It uses these collections of operators I talked about. I will formulate the full statement and I will explain it. One more parameter is introduced, some number not greater than 1, but positive number not greater than 1. And we are looking for this inequality, but for the fixed X, where the value of the function is positive. So this inequality, which is the main building block of the error bound definition, holds, provided that one of the following conditions is satisfied. The first one is for any slope, I'm using this abstract notation for an arbitrary slope operator with, I can't remember how this sign is called. So this arbitrary slope from this collection with a dagger. This collection is something where we excluded Frichet, slope. And for any slope operator from this group, this is a sufficient condition, which is pretty natural. We have a lower bound, tau is a positive number, lower bound on this slope at some u. But I will say this is not X. We require this to hold for all U, satisfying certain conditions. And I'm going to formulate these conditions. Don't pay too much attention. Don't be scared by these conditions. So the conditions look like this. So this inequality, if this inequality holds for all X satisfying all these conditions, then we have this inequality. This is a sufficient condition. What are these conditions? So for all U, such that the value of the function is not greater than the value of the function at the given point. In terms of distances, distance from U to the given point is less than this. And as alpha is not greater than 1, it means that U doesn't belong to the solution set either. So the value of the function is positive at this U as well. And two more conditions of this type. I don't want to comment on them, and I don't want you to be scared by them. I just tried to formulate the most general result. These conditions are of theoretical interest, or at least I thought that they were of theoretical interest. Surprisingly, later on, they started working when we moved to nonlinear conditions. And these type of conditions can be all of them except one, except the last one, have been used in the literature by many authors. Even this parameter has been used not too often, but some authors used it. Normally, these conditions are formulated with alpha equal 1. This is the simplest case, and everything gets simpler when alpha equals 1. But in fact, it is actually important to allow alpha to take other values, and it comes up later. This condition, it seems it has been overlooked because it is trivial. This is trivial condition, and people, including myself, up until recently, ignored this condition. But surprisingly, when we added this condition, it started working. It became important. I'm afraid I won't be able to explain all the details. Here, let me at least explain what happens with the Fréchet subdifferential slope, which has been excluded here. So here we have everything except Fréchet. That's why we have the second part, second condition, specifically when X is Asplund, and the same inequality in terms of Fréchet subdifferential slopes for all U satisfying again the same conditions, 1 and 2. The difference is only here. In the first part, we consider all U such that f of U is not greater than f of X. In the Asplund space, in the Fréchet subdifferential case, we cannot use this condition. F of U is less than mu, where mu is any number greater than f of X. So it can be taken arbitrarily close to f of X, but it cannot be replaced exactly by f of X as here. As I warned you a few minutes earlier, Fréchet setting requires some special attention, and this is reflected in this preliminary result. The importance of this preliminary result is that it actually encapsulates all the key arguments of all existing proofs of sufficient error-bound conditions. The general statement, which I will formulate on the next slide, is a trivial consequence of this one. And this practice of formulating first a preliminary condition is not new. Many people have used this approach. Probably the most famous one is the so-called basic lemma of Joffe. He introduced in 20 years ago, in the year 2000, and he discusses it in big detail in his recent book. Many other people introduced this type of conditions. I believe that this one is probably the most general. And as you can see, it is formulated for all types of subdifferential slope, all types of slopes, not only subdifferential. In your first case, I think it was formulated only for slopes in metric spaces. And the general space statement, which I promised, now we are in a setting of a complete metric space. The function is lower semi-continuous. The point is given. Tau is given, delta is given, and mu is given. So all main components present in the definition of error bounds are fixed here. By the way, just in terms of terminology, I'm talking about tau error bounds, but probably it would be more correct to talk about tau delta mu error bounds. I just don't want to break the existing terminology. So delta and mu also play a role here. We assume that they're fixed. And the theorem is, as you can see, is much shorter than the previous proposition. Again, some number is given here. Any slope operator from the whole group here. Now we don't exclude free share slopes. Everything is here. And we assume that either X bar belongs to the solution set or delta is plus infinity, which means that we cover both local and global error bounds here. So these are the assumptions. And the statement reads like this. F admits a tau error bounds with constants delta prime, and delta prime is something smaller than delta. It is delta divided by 1 plus alpha, and the same mu. So mu is given, and the same mu, provided that the same inequality which you saw on the previous slide, lower boundary for the rate of decrease of the function, and this inequality is required to hold for all u in the delta neighborhood of X bar. Delta can in particular be plus infinity. And for values of f between 0, strictly greater than 0, and the given number mu, satisfying just a single condition. So as you can see, this theorem in the linear case combines local and global error bounds. It combines primal and dual space conditions in Banach space and in Asplund space in one statement. Since we are talking about sufficient conditions, this inequality can be just dropped. So we require this inequality to hold for all u satisfying these conditions and forget about this one. This is still a sufficient condition, and in many papers, this is how error-bound conditions are formulated. These conditions is still in use by some authors, normally with alpha equal 1. Then, of course, we get standard conditions. The size of the neighborhood here is exactly 1/2 of the neighborhood where this inequality holds. So this is pretty standard and has been known probably for 20 years. When alpha gets smaller, so we have some kind of a trade-off here between the size of the neighborhood. If alpha is smaller, then this delta is getting larger, but this part is becoming smaller. So depending on applications, those who apply such conditions have a choice which alpha to use. And when alpha gets smaller, sometimes this term 1 minus alpha comes into play. And this is becoming important. I think this condition has been overlooked by all authors. It looks like we are the first to formulate it. And from the first glance, it is just a theoretical improvement. It is an improvement, of course. This condition is weaker than conventional ones, but it looks like a theoretical improvement. And interestingly, it starts working when we extend this statement into the nonlinear setting. Looking at the clock, I'm afraid I won't be able to talk much about nonlinear setting. But let me just mention what I wanted to talk about when moving into the nonlinear setting. So the linear theory is practically all here in one statement. Dozens of publications, maybe hundreds of publications, and it seems that this theorem encapsulates, I hope, all of them. In the nonlinear setting, again, plenty of work has been done, and normally people prove nonlinear conditions from scratch. My point is that nonlinear conditions for nonlinear error bounds are consequences of the corresponding conditions in the linear setting. These are illustrations, and in the Hölder setting, we actually have error bounds here, but with Q equal 1/3. I won't go into details here. This is the definition of linear error bounds, a repetition. Nonlinear error bounds look very similar, but instead of tau, I'm using some function phi here and here. Ping talked about this function 2 weeks ago. Just think of Hölder error bounds, for instance, simple case. And what to do, how to prove. This is a definition of the function. Notice that if you consider this function, linear error bounds become particular case of this one. More importantly, this function, this is a composition of two functions, and we can consider linear error bounds. This is a linear inequality with tau equal 1 for the composition. And we can just straightforwardly apply the previous theorem. This is what Azé and Karvelik called change of function. Unfortunately, I won't be able to go into details here. The corresponding conditions come up naturally by just applying the result. By default, we are using a smaller set of slope operators, but if f prime is non-increasing, which is the case in the Hölder setting, then we can use the full set. This inequality is actually, at least many people write, that this is nothing else but Kruger-Loyashevich property, which plays important role in computational stuff. I haven't checked this, but I want to think that in that computational stuff, what is important is actually the error bound property is important. And Kruger-Loyashevich property ensures error bounds. Now, unlike the linear case, we have a variable coefficient coming with the slope here. This is, of course, natural. In the linear case, phi prime is a constant, and we get back to what we already know. There appeared a series of publications by a number of authors who introduced so-called alternative error bound conditions in nonlinear setting. What are these alternative conditions about? Here, this nonlinear coefficient, it depends on the values of the function, of the given function, And the whole idea of error bounds is that the values of the function are not difficult to compute. So this is natural. In those alternative error bound conditions, instead of f of u, the authors are using something depending on this unknown set, this one, which doesn't look natural at all to me, using what we don't know in the conditions. But these authors claim that their conditions are important, and in fact, they claim that their conditions are better than the conventional ones. Now, once we introduce this 1 minus alpha coefficient, the alternative conditions become a straightforward consequence of the conventional one. They look ugly from the first glance, but this can be explained. I can't do it right now. My point is that I can prove it in one line. So these alternative conditions are consequences of the conventional ones, and the whole proof is here. It uses the fact that phi prime is assumed to be non-increasing, which is the case, as I already said, when we are in the setting of Hölder error bounds. That's basically it. I will probably stop here, just a few words of conclusions. So I talked about local and global. I introduced, King and we introduced collections of slope operators, and this allowed us to formulate universal statements, combining everything in one. We formulated 4 statements, 3 theorems, and 1 proposition. And every next statement is an immediate consequence of the previous one. So everything in the end reduces to this linear error bound statement for fixed x. So the hierarchy of all existing sufficient conditions is pretty clear. What I didn't talk about necessary conditions, but in our paper with Kung, necessary conditions make part of all these statements. I just talked about simplified versions today. The convex case, I didn't talk about it today, but believe me, in the convex case, and everything is simplified significantly, and the convex case makes a significant part of necessary conditions. And when I'm talking about the convex case, I'm talking about the convexity only of the function f, not phi. Still, phi can be a general nonlinear function, and we still have significant simplifications. We introduced, I didn't touch, and actually I don't know how to do it, special families of functions, which is of main interest of applied people dealing with applications. And this is where the main criticism of our series come from. People want recipes how to deal with particular functions arising from optimization, for example. And another interesting topic is error bounds under uncertainty. I'm not familiar with this topic, but some publications are appearing. Finally, non-lower semi-continuous case. In what I've talked about today, everything was deduced from Eklund variational principle. So lower semi-continuity was an important assumption. There appeared some publications where people treat not non-lower semi-continuous case. I can't comment on them. Just a reminder that we had a nice presentation by Abderrahim Hantout in Wombat, and he talked specifically about this non-lower semi-continuous case. I'm planning to get in touch with him, and hopefully we will find the location of this stuff within the general theory. The reference, the paper hasn't been published yet. We expect the reviews pretty soon. We submitted it in December. Hopefully they will arrive. And if the paper is not rejected straight away, we will be happy to get input from the audience of this meeting. So please let me know what you think. Feel free to criticize as much as you can or make suggestions what can be improved. Thank you. Oh, 6 o'clock. Oh, okay. Thank you.
Thank you, Alex, and for your nice presentations. Is there any common questions and criticism from the audience? So you can just unmute yourself and then ask the question. Okay, so while people thinking, so I will ask you a quick question.
Oh, you promised criticism.
Yeah. So waiting for people. I'm not.
No. You criticize.
I don't have criticism. So
okay, go ahead.
Yeah, it's like in slide 17. You have like very strange statement. Yeah. So no. The previous your general statement.
It is slide 18.
Yeah, 18. Yeah, that's one. Yep. So it's kind of strange because I like X belong to the lower set or delta is plus infinity. So why?
Okay.
Yeah.
It is not actually about this statement. It is about the definition of error bounds. Normally, everything looks like local error bounds. So if we are dealing with local error bounds, of course, we have this natural assumption X bar is a solution. If we are in a setting of global error bounds, delta equals plus infinity, then B delta is the whole space. So X bar doesn't play any role. And we don't have to assume that X is a part of the solution set. We are estimating the distance to the solution set, not in the neighborhood of some given point, but just distance to the solution set.
Okay, I see. So is that, no, just another question follow up with that. Is that equivalent if I fix an X bar like that? And then I say that this theorem satisfies for every, like for example, delta go to infinity. So they are equivalent.
No, stop.
No. Yeah.
Delta is given. Delta is fixed.
Pardon?
Delta is fixed.
Yeah. So
delta is fixed.
Yeah. Delta is fixed. I mean, so what if I change the, another property in the between? That I fix X and then I said that this condition satisfies for every delta go to infinity, for every delta positive.
Okay, this general statement makes part of a specific, we can deduce specific statements from this one, of course. And for instance, quite a natural thing is to try to find the largest tau such that this holds at least for some delta. So this is a standard conventional situation. Then we take, allow delta go to 0, not to infinity, to 0. I allow infinity specifically to handle the global case. This is a strong condition. If we drop this one, but require delta to be equal to plus infinity, which then automatically delta prime is also plus infinity, of course. And we require that this inequality holds for all u in the space. This is a strong condition. But this is the price to pay for working with global error bounds. Global error bound is a stronger property. I'm not sure whether I answered well to your question. The delta equal to infinity should be handled separately. We just allow it to be part of the general statement.
Okay. Yeah, anyway, thank you very much for your answer. I will think about that in details and then we will discuss later. So we have another question from Second. Yeah, so.
Okay, Dukhan.
That's
What's the question?
Problem.
Evgeny. Okay.
Yeah. Do you hear me?
Yeah, I can hear you very well.
Yeah. Actually, I have two questions. First of all, it's a little bit strange that we are talking about errors, but using all the time the exact values of f and gradients. This is kind of misleading. Aren't we talking about the variances of a function more than errors? But that isn't just a terminology, of course. But my second question is that there is now quite a lot of work on inexact oracles in optimization and things like that. Do you see any connection between these inexact oracles and these error bounds theorems and results?
Thank you, Evgeny, for your question. I'm not sure whether I understood your first question well. The operator, the slope operator here is not fixed. You can choose any slope operator here. And even the value is not fixed. We only have a lower estimate. If this lower estimate in terms of tau holds, we have error bounds. Of course, for all u satisfying the given conditions. This is your first question. The second one with fuzzy sets, so maybe my interpretation is not correct. This is probably related to what I was talking about in the very end.
It's not fuzzy.
Error bounds under uncertainty, for instance.
Yeah,
this can be interpreted. I don't know how to do this. I mentioned related topics, which I don't know how to handle. But I do know that such publications exist. Sorry, I already mentioned that the main criticism of all these general theories come from people who work with practical problems and want to get practical immediate recipes. I'm only trying to bring order in the variety of existing conditions. Although I do know that such publications exist, and I do know people who work on that, and if you are interested, I can connect you with those people.
I see, thank you. Mm-hmm.
Tao had to leave, okay, thank you. So apart from thanks, I don't see anything else in the chat.
Yeah.
Dukha, thank you for your thank you, okay. Any more? Chairperson. Any more comments, results, criticism?
So if we don't have any question for Alex, so I think we should close the seminars here. So thanks Alex again for setup and for the very nice talk.
Thank you everybody for coming, especially people from Europe who had to wake up so early to attend
this
talk.
Thank you, Marco, for trying to connect to
Marco, thank you very much for coming. This, by the way, arose from our joint paper with Shaoqi. This was like a predecessor. Okay, thank you everybody.